The Nearly Perfect Prediction Theorem. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading a very short article called The Nearly Perfect Prediction Theorem by Joel David Hamkins, published in 2025 in the notices of the AMS. Like stock market traders trying to guess today's opening price and movements, we aim to predict the current and future values of an unknown function based on the observed history of previous values. The true function f from the reals to the reals, not necessarily continuous, will be revealed only gradually. The Nearly Perfect Prediction Theorem, a remarkable result of Christopher Hardin and Alan Taylor, shows that there is a nearly perfect prediction strategy predicting the current and immediate future values of every function almost always correctly. Oh, really? That sounds too good to be true. Let's see what this is about. For predicting the present, we define a prediction strategy, big P, which takes finite segments, or which takes initial segments of the reals to the reals. On this, it's defined on the set of initial segments, which we think of as possible histories, written as f restrict t, where t is a real number and f is a function from the reals to the reals, and f restrict t for the restriction of f to the open interval from minus infinity to t. For every function f from the reals to the reals, these predictors are almost always correct, by which we mean that f of t equals big P of f restrict to t, presumably for almost all t that's left unwritten. Specifically, the predictions will be correct except on a countable nowhere dense set of exceptional points. What's more, every real number s will be followed by an interval from s to s plus epsilon on which the predictions are correct, and indeed there will be arbitrarily long intervals on which the predictions are perfectly correct. It's incredible. To define the prediction strategy, simply fix a well-ordered triangle less than or equal to on the set of all functions f from the reals to the reals, and let big P predict in accordance with the triangle less than or equal to least functions standing in agreement with the observed data. That is, given historical information f restricted to t, let big P of f restricted to t equals f star of t, where f star is the triangle less than or equal to least function compatible with the prior data, meaning that f star restricted to t equals f restricted to t. Here, the author is implicitly using the axiom of choice in one of its equivalent forms, namely the statement that every set can be well ordered. To see that these predictions are almost always correct, suppose that the true function is f from the reals to the reals. As time passes, more of the function is revealed, and so the class of compatible functions becomes more restrictive. Consequently, s less than t implies f star s triangle less than or equal to f star t, where these are the triangle less than or equal to least functions in agreement with the data at those times. Further, if the prediction at time s is incorrect, then f star s would be incompatible with the data up to t, and so f star s not equal to f star t. So the prediction functions climb strictly higher in the hierarchy. F star s is strictly triangle less than f star t at every exceptional point, and since this hierarchy is well ordered, the exceptional points themselves must therefore be well ordered in the real numbers. From this, all the amazing consequences follow. Above every real number s, there is a next exceptional point, if any, and so there is an open interval from s to s plus epsilon on which all the predictions are correct. The exceptional points are thus a countable nowhere dense set, countable since we can associate each exceptional s with a rational number in this interval. Since there must also be an absolutely smallest exceptional point r, if any, all predictions made at times t before r are correct, and so there are arbitrarily long intervals on which all the predictions are correct. The real line is thus exhausted by a countable, well-ordered sequence of intervals, which abut each other and their limits, with the predictions fully correct in the interior of each interval. Amazing. It is indeed kind of amazing, and it's funny how simple the proof is, too. A brilliant application of the well-ordering principle. Anyway, the author continues, Next, to predict the immediate future values of the function, we extend our earlier idea to defining a continuation prediction strategy, big F, from initial segments of the reals to sets from the reals to the reals, which maps each history, f restricted t, to its predicted continuation, big F of f restricted t equals f star, the triangle less than or equal to least function standing in agreement with the observed data f restricted t equals f star restricted t. There's a figure which shows pictorially what's going on. Incredible as it may seem, these predicted continuations will almost always agree with the true function f in an interval extended strictly beyond t. There exists an epsilon bigger than 0 such that for all x less than t plus epsilon f of x equals big F of f restricted t quantity of x. We observed earlier, in effect, that if s less t, then big F of f restricted s is triangle less than or equal to big F of f restricted t, since any function compatible with the later data f restricted t is also compatible with the earlier data f restricted s. As time passes, therefore, we're climbing in the delta less than or equal to hierarchy, and we climb strictly higher whenever the prediction at s is not fully correct between s and t. So again, the continuation prediction exceptional points will be well ordered in the real numbers, and consequently, again, they will form a countable nowhere dense set. So the continuation predictions are almost always correct. And again, following every point s will be an interval, the open interval from s to s plus epsilon, on which all predicted continuations are correct for the duration. And there will again be an absolutely least exceptional point r, meaning that the predicted continuations are fully correct for the entire interval from minus infinity to r, which includes arbitrarily long intervals on which the predictions are correct. I find it interesting to notice a certain robust stability. Whenever a correct continuation prediction is made, then the very same prediction will continue to be made for the duration of that correctness, since it will continue as the triangle less than or equal to least function in agreement with the observed data as long as it remains correct. The theorem is interesting even just for continuous functions. Although predicting the present value f of t of a continuous function is trivial, of course, since it is just the limit of f of x as x goes to t from below, the nearly perfect prediction theorem enables us to predict how a continuous function will continue into the immediate future, which is not trivial. We can ensure that strategies big P and big F predict in accordance with continuity when possible simply by placing the continuous functions at the bottom of the triangle less than or equal to hierarchy. Meanwhile, the reader will have noticed that the proof of the nearly perfect prediction theorem is not constructive, since it relies on the axiom of choice via the well-order theorem. The proof does not provide a useful concrete prediction strategy. It reveals little about the actual predictions to be made. I regret to say that you had best keep your day job. Rather, we proved the theorem as a pure existence result, showing that there is a nearly perfect prediction strategy as a matter of abstract mathematical ontology. I am confident that the iridescent mathematical stock traders of the Platonic realm are truly making bank. I like this Hamkins guy. I've read numerous papers by him before and cited some of his work as well. And this is indeed a very clever work. Is it due to Hamkins? No, it is not due to Hamkins. He is merely reporting on it. It is due to Christopher Hardin and Alan Taylor. But this is a very beautiful piece of mathematics here, showing how using very simple mathematical logic you can get really stunning, nearly unbelievable results. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. I'll see you in the next video.